Okay, there we go. Hello. So first, does anybody have any questions? Let's bring up the chat and you can ask them in the chat box or unmute if you have any questions. Okay. If there are any questions throughout, I have my chat box up so you can definitely ask. So today I'm just going to be going over the kind of things you'll be seeing on the exam, but I highly encourage people to stop me if you want me to go more in detail on any of the topics. I will kind of review everything, but quickly. But anything you guys want me to go further into detail, just let me know. So we're going over, this is modules 5 and 6 for the exam, which is chapters 3 and 4 in the book. So we're looking at reactions, specifically aqueous reactions, and a lot of this is going to be what you already saw on the take-home, because a lot of it's math-based. But I'm going to point out some of the things that you should know for the actual test, the in-person portion of the test. First, you should understand the law of conservation of mass. With the law of conservation of mass, that's why we do balancing of equations, because whatever we have on our reactant side, we're going to have everything the same on our product side, just rearranged. A chemical reaction only rearranges atoms. It doesn't destroy atoms or produce atoms. So the only way that we can make or destroy atoms is with nuclear reactions. So besides what we looked at with module 17, all the rest of this is going to be conservation of mass. So you should be able to look at a chemical equation. You should be able to balance that chemical equation. There's not going to be a lot of math on this exam, but there may be small amounts of math that you would need to do. Balancing could be part of it. You should know how, sorry, 1 second. Okay. You should know what the components of a reaction are. So you should know the left side is the reactants, the right side is the products. You should know that S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous. So these are the different states you might see in a chemical equation. Aqueous specifically means dissolved in water. Right? So you should know if I give you a chemical equation, especially if it's a precipitation equation, you should be writing all the states if I wrote the states or told you to write the states. Let's see. So you should balance components. You should know the different reaction types. So you should be able to look at these different reactions and be able to identify them. So we've got decomposition reactions. So that's where you have some substance that breaks down into 2 or more substances. You have one reactant, 2 or more products. We have a combination, which is kind of the opposite of this, where you have 2 or more reactants. And actually, let me do an example first. So we can have A plus B going to AB. So 2 or more reactants. going to one product. They're combining. We have a metathesis reaction. With our metathesis reaction, we're specifically looking at what's called a salt metathesis reaction. There are other types. If anybody takes organic, you'll see other types of metathesis reactions. With metathesis reactions, you are essentially just switching partners. So AB plus CD goes to CB plus AD, something like that. This is called a double replacement reaction as well. And if our product is a solid, if we have a solid product, from two aqueous reactants, this is a precipitation reaction. So this will be AB, AQ plus CD, AQ goes to CB solid plus AD, AQ. You should know the solubility rules. So make sure you go through those solubility rules. We will be doing precipitation reactions on this exam. So you should know your different rules for those. So make sure to review those before the exam. Then we also have something called a single replacement reaction. We have A plus BC goes to AC plus B, something like that. And one type of single replacement reaction, and not all of these are single replacement reaction, but not all of these are single replacement reactions, but often we see redox reactions within here where we have a metal plus metal salt, and they are going to do a single replacement. Not all redox reactions are single replacement reactions, but a lot of them are if we have just a metal reacting. But some of the redox reactions end up being double replacement reactions as well. Oh, and then we have acid-base neutralization reactions. Where you have some acid reacting with a base, and generally you're going to produce water and a salt. I guess I should do P. Sometimes you get OH. Go with that. You'll produce water and a salt for most of these acid-base neutralization reactions. There are many different types of bases that are used in these acid-base neutralization reactions, and only one general acid, just HA. So anytime you see an H at the beginning, generally you're dealing with an acid. Not 100% of the time, as we can see with water, but generally if an hydrogen is at the beginning, it's an acid. But we have different types of bases. We have hydroxide bases. So that would be a BOH. And with a BOH, we're going to produce water and a salt. when we react with an acid. We have a sulfide base. So a sulfur-containing base that when we react with an acid produces hydrogen sulfide and a salt. We have a carbonate base where we have CO3, carbonate, right? And in this case, we'll produce water and salt and carbon dioxide. And then a bicarbonate base. So bicarbonate is HCO3. So it's got some cation with it. And it produces the same exact products: water, salt, carbon dioxide. So you should know the products of these bases. So you should be able to do acid-base neutralization reactions with any one of these bases. The acids, like I said, they won't change. It's just the bases that change. And depending on the base will determine what your products are. These last three are called gas forming. They're gas forming neutralization reactions because H2S is a gas and then CO2 is a gas. Okay. You should be able to determine molar mass. I don't think there's going to be much in the way of stoichiometry on this, but you should still be able to determine molar mass. You should understand what a limiting reactant is. So, know how to determine molar mass. If you've done the take-home exam, you should already know. We did lots of determining molar mass on there. And you should know what a limiting reactant is. I often call it a limiting reagent. They're the same thing. And you should know what theoretical yield is. You should know what percent yield is. And you should know what percent error is. So you should be able to, at the very least, tell me what the equations are for all of those. And that's it for Module 5 or Chapter 3. With Module 6, are there any questions real quick? Okay. So if there are no questions, let's look at Module 6 or Chapter 4. In this one, this is just aqueous reactions. So a lot of the different reaction types I talked about actually come from the Module 6 or Chapter 4, but I just pointed them out there. Within Module 6, you should know what a solute is. So that's in greater quantities. Or sorry, yeah, I said solute. I meant to say solvent. Solvent in greater quantities in a solution. And then the solute is in lesser quantities. So these are the two components of a solution. So you have the solvent, what you dissolve the solute in. You'll always have a greater amount of solvent than you have a solute. You only have one solvent. You can have 2 or more solutes if you would like. Generally, the stuff we look at will only only has one solute. You should know what an electrolyte is, what a non-electrolyte is, and within electrolyte, you should know weak versus strong. Okay. So weak electrolytes, these are going to be weak acids and weak bases. Strong electrolytes are going to be strong acids, strong bases, and ionic compounds. And then non-electrolytes are going to be all molecular compounds, or all molecular species rather. All molecular species except acids and bases. Okay? You should understand the dissolving process of a electrolyte, whether it's weak or strong versus a non-electrolyte. So if we have something like sugar, table sugar, C12H22O11, when we take that and we dissolve that in water, it's going to remain that molecule. But now it's going to be aqueous, right? So in a sugar crystal, each of the molecules of sugar are connected to other sugar molecules that we would call intermolecular forces. And we'll learn much more about intermolecular forces in Chem 2. But these are not bonds, these are just interactions. And they're pretty easily broken up when you dissolve the species in a solvent. So you will just lose those interactions and you're just going to have water hanging out around, right? So you had them all together, held on by these electrostatic interactions, and then the water surrounds each of the molecules instead. If we're talking about an ionic compound, something like sodium chloride, when we take it and we add in water, we break apart into ions. And it's going to break apart entirely into ions. So there will be no sodium chloride units left together. We'll learn more about that. So we consider this to be completely disassociated. Disassociated. Sorry, I can't spell. So they're going to break down completely into ions. So for every 1 mole of sodium chloride that you start out with, you produce 1 mole of sodium ions and 1 mole of chlorine ions. So there is no intact sodium chloride. The difference here is you have it's with sodium chloride, these are ions that are held together by ionic bonds. And it's this 3-dimensional structure that's a bunch of bonds. And then as you dissolve, you produce these ions that are surrounded by water molecules. A solvation sphere. So they dissolve completely differently. When we dissolve something like sugar, we don't produce any ions. So we make a non-electrolyte solution, something that cannot conduct electricity. When we take something that's ionic, we break it down, it's going to break down into ions, and those ions can conduct electricity. So this is why this is an electrolyte solution, and this is a non-electrolyte solution. A strong acid or strong base will do the same exact thing. So we have some acid, we put it into water, it'll break down into hydrogen ions and the anion, and it will completely dissolve. It'll completely dissociate, breaking down into ions. So you start out with 1 mole of your acid or your base, you produce 1 mole of each of your ions. A weak acid or a weak base this is going to be an equilibrium process. Sorry, I'm spending so long on this dissolving process. I feel like it's a very important topic. And since we're an online class, I don't get to go over this very much. So weak acid and weak base, instead of completely dissociating, some of it will dissociate. And we can show that using a two-way arrow. So it's either like that, or you can see it like that, or sometimes it'll be written like this. All three of these are the same. So some of it will break down into ions, but some of it will remain intact. So you'll have some of this in solution, some of this in solution, and some of this in solution. So after you dissolve it in water, you have HA, A minus, and H plus all in solution. So that's why it's called a weak electrolyte, because only some of the species is breaking down into ions. I've already talked about it, but you should know your precipitation rules. And with a precipitation reaction, or any other reaction where we're producing something that's not aqueous, you should be able, something that's not aqueous and it's kind of made of salts or acids, you should be able to write a chemical equation. So precipitation reactions and acid-base neutralization reactions. So for both of these types of reactions, you should be able to predict the products. You should be able to, as such, write the balanced chemical equation. And you should be able to write the complete ionic equation along with the net ionic equation. And you should be able to determine spectator ions. And I can show this with something like this. So hydrochloric acid will react with sodium hydroxide to produce water, which is a liquid, so something other than aqueous, and sodium chloride, which is aqueous. Keep in mind, anything that's in the aqueous state, if it's ionic or a strong acid or a base is really just ions in solution. So all of these, all the things that are ions are going to break down, are actually going to be ions in solution. So when we go to our, sorry, 1 second. When we go to our complete ionic, anything that's aqueous that is strong acid, strong base, or ionic will break down into ions. So this is actually H plus AQ plus Cl minus AQ plus NaOH plus AQ plus OH minus AQ goes to H2O liquid, right? That's a molecular species. It's not going to be broken down in ions, and it's not a solid. And Na plus AQ. I now realize that I should have left more room. There we go. Plus Cl minus AQ. So this would be a neutralization reaction where we've got ions all over the place. We can see that this sodium and this chlorine are the same on both sides. That makes them spectator ions. So when we get to our net ionic, we would remove them and it would just be H plus AQ plus OH minus AQ goes to H2O liquid. Are there any questions about this? This is definitely going to be on the test. Okay. We can also do this for precipitation reactions. So lead nitrate by solubility rules is soluble. All nitrates are soluble. Potassium iodide is soluble. All alkali metal complexes are soluble. When they combine, we're going to switch partners, right? So this is our A, B, C, and D. So we're just going to switch partners. We're going to produce lead iodide and potassium nitrate. Potassium nitrate, that by solubility rules is soluble. Sorry. Undo. Let's try that again. This is very horribly written. But if we look on our solubility rules, iodide compounds of lead are insoluble. So that would be our precipitate in this case. So that would be the solid. So aqueous, 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 those are all going to break down in ions in our complete ionic equation. So we'd have Pb2 plus, oh, sorry. You put a 2 there to balance it. Pb2 plus 2NO3 minus. So because this is here, it's going to go here. So any subscript is going to come out. And then anytime we have a coefficient, it gets applied to all ions. So plus 2K plus AQ, sorry, AQ plus 2I minus AQ. So as we see, that 2 gets applied across. Also note, with these ionic equations, all charges are shown, all states are shown. And then anything that's not aqueous, so if it's a gas, a solid, or a liquid, we're going to keep it as that species. And then plus 2K plus AQ plus 2NO3 minus AQ. So again, having that apply across to both of them. So anything that's a spectator ion same on both sides, are going to be canceled out in the net ionic Okay. So, any questions about this? Okay. We've already talked about acids, bases, neutralization reactions. Redox reactions. You should know what oxidation is. So no definitions for oxidation, right? Loss of electrons, reduction, gain of electrons, oxidizing agent, the species that contains the thing that's reduced, reducing agent, the species that contains the thing that's oxidized. Keep in mind with oxidation and reduction, this is an atom, right? I mean, it could be 2 or 3 iron atoms or iron ions. So atom or monoatomic ion. So when we talk about something being oxidized or reduced, we're not going to put a compound in there is what I'm trying to say here. But with your oxidizing agent or your reducing agent, this could be atom or compound or molecule. So for both. So if we have, I don't know, see an example of one. There we go. Mg plus, actually no, I don't want that one. Fe plus NiNO3 goes to FeNO3 plus Ni. The nickel is being reduced. The iron is being oxidized. So Fe oxidized, Ni reduced. Our oxidizing agent, it's going to contain the thing that's being reduced. That would be nickel nitrate. And then our reducing agent, that contains what's being oxidized, would just be iron in this case. Any questions about that? Okay. You guys will not be balancing redox reactions. You did that on the take home, but you should be able to identify if things are being oxidized or reduced. You should be able to identify the oxidizing or reducing agent. Okay. For concentrations, you should understand, you should be able to give a definition for molarity, right? So moles of solute divided by liters of solution, right? Where it's solute plus solvent, right? Total volume of your solution. So you should know what molarity is. You should understand how to determine the concentration of a compound, molecule, or an ion. So if we have something like iron hydroxide, iron 2 hydroxide, we throw that in water, we produce iron ions, and 2 hydroxide ions. Let's say we start with 1 molar iron hydroxide, iron 2 hydroxide. Our ion concentration would be 1 molar for Fe2 plus, but 2 molar for hydroxide ions because of that 2 right there. So you should be able to determine the concentration of ions in solution. You should know what the dilution calculation is. So you should know what M1V1 equals M2V2 is and how to use it. So this be concentration and volume of stock solution. So whatever your stock solution's concentration is, and then how much of that stock solution you're going to dilute. M2 is your desired dilute concentration. You cannot concentrate, you can only dilute. And then our V2 is your final desired volume. So you should be able to describe how to make a solution, how to do a dilution, how to make a solution and how to do a dilution, thinking about molarity and your dilution calculation. Last thing that's in this chapter or module is the idea of titration. So with titration, you should be able to define titrant, analyte, equivalence point, and what an indicator is. So titrant, that's our unknown concentration solution. So in a titration, we have a set volume of that. So it has a known volume. And we're trying to determine the concentration of a titrant. And then we have our, oh my God, I screwed that up. That's our analyte. Sorry about that. Boop. That's the analyte. Our titrant is a thing that gets titrated. So our titrant, that has a known concentration. It's also called the standard solution. And we add in titrant until we get to our equivalence point in order to determine the concentration of the analyte. So our equivalence point is when our moles of titrant is equal to the moles of analyte, keeping in mind a balanced equation. What I mean by that is if we have HCl plus NaOH producing NaCl plus H2O, when our moles of HCl are equal to our moles of NaOH, that is our equivalence point. But if we have something like H2SO4 plus 2 NaOH going to 2 H2O plus Na2SO4. We have 1 mole of H2SO4 and 2 moles of NaOH. They are stoichiometrically coefficient or stoichiometrically equivalent. So this would be at this point, we'd be at our equivalence point. I guess we're at 1 to 2. So when they are stoichiometrically equivalent, our moles of with our titrations, we're looking at their acid-base titrations. There are others, but we're not going to look at that this semester. But when moles of acid, moles of base are equivalent stoichiometrically, we are at our equivalence point. One last thing, pH. You should know that a pH of an acid is less than 7. pH of a base is more than 7. And if we have a neutral solution, such as what you get from a neutralization reaction, when we are stoichiometrically equivalent. This is not always true, but for this semester, when they are stoichiometrically equivalent in a neutral solution, that is going to be a pH equal to 7. And that is everything that's going to be on the test, or everything that could possibly be on the test, I guess I should say. Does anybody have any questions? Anybody need me to go over anything more in detail?
If we have questions about our take home, do we email you separately?
Yes.
Okay.
And if you guys do have any questions about your take home, please do email me. I don't mind questions. I may not give full answers, but I will always be willing to give some sort of answer. Okay. If nobody has any questions at this moment, let's call it good. But if anybody does have any questions, email me. Let me know. And good luck. I'll see you guys tomorrow at 8 a.m. Thank you. You guys have a great day. Oh, in case I forget to mention this, I'm going to try and remember to mention this, but if you guys attend SI sessions, I will start giving extra credit points for tests. I don't know if I said that already. Did I say that already? Anybody know? I don't remember if I had said that or not. But if you guys start attending SI sessions, oh, I did. Okay, so I did say that before. Okay, so every SI session that you attend before an exam, it'll go to that exam, and then the next set will go to the following exam, and so on and so forth. Okay, you guys have a great day. Email me with any questions you might have. Bye, everybody. Oop, that didn't work. Why would it work?